Good evening, everybody. I'm Rick Gering, and we're going to spend a little time under some virtual stars tonight. There we go. The first thing we need to talk about when we're talking about what you can see in the sky from your backyard in the suburbs is why there are so few things we can see these days. And for that, we've got to go back in time. About 50 years ago, this was your grandparents' sky. I didn't grow up in Naperville, but enough people have told me this that I believe it to be true, that in the late 60s and in the first half of the 70s in Naperville, if you went out in your backyard at night and you looked up, you were able to see the Milky Way. And for those of you who have no idea what that means, that sort of amorphous, frankly, milky-looking thing that's going across the screen from lower right to upper left is the Milky Way. It's the looking outward through the disk of our galaxy. 50 years ago, you could see it from Naperville. And today, well, your children's sky is a little less inspiring and not quite as impressive. So how did we get here? How did we mess it up this bad? Well, to understand why we have trouble seeing the stars, one thing we need to do is to start thinking about things from the stars' perspective. And this is how we look to them. If you Google Earth at night, you'll find all kinds of images taken from satellites that are stitched together into mosaics like this one. And while people generally say, oh, look, you can see Chicago and you can see the Nile River and so on, when I look at this, I just feel sad. And I think you should feel sad as well, because what we're seeing in these photographs is the light that's seen by satellites in Earth orbit. It's light that goes straight up into the air. It is light that literally is doing no earthly good. And it's not magic light. It isn't created out of nothing somehow. It's light that is generated by the same energy at the same cost as the light that you're using right now to light your homes. And if you look at this photograph of the U.S., this was around 2009. It's a little bit worse now. This is how much light and how much energy and how much money we are wasting night after night, 7 nights a week, 365 nights a year. And if we could save half of the money that we're wasting on this energy, or the energy that's going into these lights, just imagine what we could do. So where does all this light come from? Well, it mostly comes from bad, thoughtless lighting design. If you look around at the fixtures that are used for outdoor lighting, you'll probably be amazed at how many of them are nothing more than what we see on the left edge here. The glass globe that sends light up, down, left, right, in, out, pretty much everywhere, whether it needs to be there or not, and whether it's doing any good or not. What we should be doing with light is throwing it down where it will do some good for us, as you see on the right end. And while we're not here to talk about light pollution tonight, although we could spend 2 hours without any problem just talking about that, let me just get it down to one slide for you. What causes light pollution? Well, first, poorly designed light fixtures. Light should go down, shouldn't go sideways, because that's just glare. It's the light that makes the center fielder drop the ball. And it should never go up, because that's just waste. It results from poorly thought out lighting plans. If we were thinking about what we were doing, we would put light only where it's needed, in the amount that it's needed, and when it's needed, and then we would stop. It comes from excessive blue light, for those of you who have been sitting here thinking, oh, this guy doesn't know what he's talking about. LEDs are going to fix all these problems. Well, you know, to a large extent they could, except for the fact that when we were using LEDs, two things happen. First, they put the same amount of power into the LEDs that they put into the conventional fixtures beforehand, which means that they're not saving any energy and they're creating even more light. And second, LEDs tend to be designed in a way that pushes the color balance far towards the blue end of the spectrum. And why is that done? Well, because it looks cool. Well, maybe it does, but it also has the greatest deleterious effect on the sky, on humans, and on other species. So what does light pollution cost? Well, it costs wasted energy, which often has its own associated pollution. It costs wasted money, because the energy that creates light pollution is not free. It causes the loss of nocturnal species habitat. And before you say that you don't really worry too much about the bats, it's not just the bats, it's 70% of mammals are nocturnal, and most bird migration occurs at night. Light pollution affects all of that. It certainly has effects on our circadian rhythm, and while I've left a question mark after the effect of light pollution on human health, there are a growing number of people who would want to change that question mark into an exclamation point. And the most important point that I would make about light pollution is this last one. If you don't remember anything else about light pollution from the night, I hope that you would just remember this. It doesn't cost a dime more to do lighting in a way that doesn't ruin the night sky. So why does light pollution ruin the night sky? Well, you know, we say as we sit outside and the sun goes down and starts getting dark, we say the stars are starting to come out. Well, of course they're not, because the stars are always there. It's just that as the sky gets darker, we start to be able to see them. And the darker the sky gets, the more stars we can see. And it works the other way as well. If the sky never gets dark, then you never see stars. And if it never gets as dark as it used to, then you never see as many stars as you used to. And that's pretty much what we're looking at today. You can see in the series of views on the screen everything from the complete absence of stars if you look up in downtown Chicago, all the way to the other extreme, the kind of sky you would see in the middle of the desert. And of course, since astronomers are often basically engineers at heart, somebody had to put that on a numerical scale. An astronomer named John Bortle did that about 20 years ago and created a scale that runs from Bortle 1, which is basically a desert sky, up to Bortle 9, which is basically downtown Chicago. And when we talk about Bortle ratings, we generally talk about colors rather than numbers. And on this scale, what you're really looking for, if you want to see things in the sky, you really like to see Bortle blue or darker if you can. Unfortunately, in this part of the country, Bortle blue is pretty much gone. This again is a light pollution map that's several years out of date, so it's worse now than it was at the time this was made. But even when this was created, you can see in the area near Chicago, you have to get down into Missouri before you run into any Bortle blue. And this is a close-up if you'd like to know what the sky's like in your backyard. You can see the west suburbs over there on the right under the bright white lights. We're basically not much better off than downtown Chicago. And you can get a sense of how far you have to go well past Route 39, even to reach Bortle green skies in this part of the country. With that being said, there's still some things that you can see from your backyard in the suburbs. So let's talk about them. First, we've got a group of targets that you can visit all year long: the sun, the moon, and the International Space Station. We have targets that come back predictably every year, which are meteor showers, stars, and deep sky objects like star clusters, galaxies, and nebulas. And then we have targets that come and go on their own schedule, comets and planets. So let's start with the ones that are always there: sun, moon, and the space station. Right now, we are just coming out of the quietest part of the solar cycle, and it's been a long drought since we've seen a lot of sunspots. In a small telescope with a normal filter on it, you'll be able to see sunspots which have the dark umbra and the not quite as dark penumbra, and you can see a little bit of granulation, which is sort of the orange rind texture that you can very subtly see in this image. What you're seeing in the orange rind texture is light areas where columns of hot gas are flowing up from inside the sun. They reach the top of the gas part of the sun, spread out, and they start to cool. And then the darker areas are where the cool gas is flowing back down into the sun, where it'll get warmed up, pushed back up in one of those light-colored columns, cool out and go back down again, which is basically the same thing that happens when you boil a pot of water on your stove, although the sun's doing that at a much higher temperature of about 10,000 degrees Fahrenheit. When you view the sun in a telescope or anything, any kind of device, the most important thing is doing it safely. And what we see in the stamp here is exactly what you do not want to do, which is to point a telescope or a binocular or any kind of device, or even your glasses for that matter, at the sun with no filter. The only reason the fella looking through that telescope is not screaming in agony right now is that his retina is not wired for pain, doesn't have sensory nerves. But what's happening inside his head is basically what you see happening here. If any of you have ever been a 7-year-old boy, you've done this. You take the magnifying glass, you make the sun come through the magnifying glass, and you set the dry leaves on fire. Well, a telescope is basically just a big magnifying glass. The sun is the sun, and if you look at the sun without a filter, that leaf is your retina. And since your retina does not have sensory nerves, the first notice that you're going to have that something is wrong is when you can't see out of that eye ever again. So we don't want this to happen. So how do we avoid it? Well, we'll talk about that in a minute, but first I want to talk about another way that we're not going to avoid it. For a long time, I didn't think I needed to talk about these anymore. This is something that came about back in the 70s. Telescope manufacturers used to sell what they called eyepiece sun filters, which was a little piece of filter glass like this that screwed into the end of an eyepiece and would then go into your telescope. Well, if you think about what's happening inside the telescope, when the sun hits that lens at the end, it generates an awful lot of heat, and that heat collects inside the tube, and the eyepiece is sticking into the tube, and that glass filter is at the end of the eyepiece, and what happens is what you would expect. There's a fella in England who posted a YouTube video a while ago where he took one of these eyepiece sun filters, put it in his eyepiece, put it in the telescope, pointed it at the sun, and started his stopwatch and his video camera. 2 minutes and 54 seconds later, he noticed that there was a bright white spot in the center of the eyepiece field. And that happened because the heat inside the telescope, after less than 3 minutes, became great enough that it shattered the glass of the filter. Part of a piece of the filter fell out, as you can see in the right-hand picture, and allowed the unfiltered sunlight to come through. And I'm happy that nobody was looking through that eyepiece when that happened. Like I said, I used to not have to talk about that because after the 70s, it was sort of like disco. We figured out that maybe it wasn't the best idea we ever had. But now it's back through the wonders of electronic commerce. You can buy eyepiece sun filters on eBay, and you can buy them on Amazon too for less than $5. And what I find most galling about it is the fact that the people who are selling them absolutely know that what they're selling is useless. The language in red on the right is taken from the eBay posting. And it says, please use with Bortle solar film sun filter to protect your eyes. Well, we're going to find out in a minute. If you're using a Bortle solar film sun filter on your telescope, you don't need anything else to protect your eyes. So it's sort of like selling umbrellas and saying, use only while wearing a raincoat or you'll get soaked. So if you have a telescope and you're tempted to buy one of these, please don't. If you have a telescope and you own one of these, please throw it away. And if you are going down the street and see someone with a telescope who's offering to let you have a look at the sun, what you want to look for is what we see in this picture. And that's a full aperture solar filter at the business end of the telescope. What's important is that the filter has to be the first thing that the sunlight hits before it enters the telescope. And if that's what you see, then it's a safe setup. And by all means, take a look at the sun because it can be pretty cool. And if you are a person with a telescope who is offering views of the sun to people, please use only a full aperture solar filter on the front end of the instrument. And also, as we see in this picture, I give this guy extra credit because he did have the foresight to put a cover on his finder scope there on the left of the tube, because I guarantee you, if you put up a telescope and start letting people look through it, within a nanosecond of the time you turn your back, some 6-year-old will try to look at the sun through the finder scope, and you either want to have it removed or capped off to make sure that you don't have a disaster. So much for the sun. What about the moon? Well, we can look at the moon. We don't need a telescope. You can see the moon naked eye, obviously, and we can see basically only 3 things about the moon naked eye. The light areas on the moon, the highlands, are the moon's original surface. They're sort of the gray areas. The Maria, which is the plural of the Latin word mare for sea or ocean, are the dark areas. And as you look at them, you can see a lot of them generally tend to be big and round, and they look like oversized craters. And that's because basically that's what they are. During the moon's formation, really, really big stuff ran into it and left huge, hundreds of miles across basins. They're too big to really call them craters, but basically hundreds of miles wide craters that disrupted the moon enough that lava started flowing up from inside the moon through the floors of the basins and filled them with literally miles deep lakes of lava that subsequently hardened into a rock called basalt, which is nearly black, and that's how we got the dark areas of the moon. It's all lava that is hardened into the dark rock. The third thing that we can see on the moon naked eye is the rays from some of the major craters. The most obvious one is the crater Tycho, which is the guy you see down at the lower right part of the moon. It's a fairly young crater on the moon, and what happened was that a large object, not as large as the ones that formed the mares, but a reasonably large object hit the moon, left a hole in it that was 50 odd miles wide, and dug up a bunch of the lunar surface that was just below the surface of the moon. The gray color that we see in most of the highlands is a little darker than the moon's, if you want to think of it as the moon's original color, because the moon has been constantly pulverized by micrometeors that have, you could say, they've dirtied up the surface a little bit. So the very top layer of the lunar surface is a darker color than the stuff right underneath it. When the Tycho impactor hit, it splattered out a lot of this material from just under the surface and threw it literally hundreds of miles. And you can follow its path in those long white rays that come out of Tycho. And as I say, there's one of them that is over 1,000 miles long. It was must have been a pretty impressive sight when it happened. I'm glad I wasn't there. You can look at the moon in binoculars, but I recommend against it unless you have your binoculars on a tripod. You will never be able to hold binoculars steady enough, hand holding them, to be able to actually make out any of the craters on the moon. If you do have binoculars on a tripod, they can give you a little better view than you get just naked eye, but generally binoculars are not the best choice for looking at the moon. Small telescopes, on the other hand, will allow you to see literally hundreds of craters in quite a bit of detail. And when we look at the moon in a telescope or in binoculars, we want to look along this line called the terminator, which is the line where light and dark meet on the moon. And if you think about why half the moon is light, it's because the sun's lighting it and it's daytime there. And the terminator is the line where sunrise and sunset is happening on the moon. Sunrise on the part of the moon that's rotating towards the sun, sunset on the part of the moon that's rotating away from the sun. And just like on Earth, the longest shadows on the moon happen at sunrise and sunset. When we look at features on the moon, we're able to see them because of the interplay of light and shadow. And therefore, when the shadows are longest, the detail or the features are most detailed. So if you look at the kinds of things you can see in a small telescope, if you look at craters on the moon, if you look at the picture in the center, that's the crater Copernicus, and you can see some of the very intricate and sometimes very, very interesting terracing on the walls of the crater, where material has started to slump down into the crater along the walls. You can see the central peaks in the middle of the crater, where the impactor pushed the moon's crust inward, and the crust subsequently rebounded outwards, forming those hills that you see in the center. Just to put the crater there in perspective, Copernicus is about 58 miles wide, and it's 2.5 miles from the top of the crater wall down to the crater floor. It would be a heck of a climb if you had to get out of there on foot. And those mountains in the center are about 1.5 miles tall. So they're pretty impressive features. And if you compare Copernicus to the crater that we see in the top right picture, which is a crater called Plato, Plato is 63 miles wide, and it's very much like Copernicus in some respects. And it probably looked almost exactly like Copernicus shortly after it formed, but in the years that have happened since then, somewhere along the line, the floor of Plato split, and lava was allowed to flow up from inside the moon into the crater, so that today, again, we see this dark basaltic rock that is formed across the floor of Plato. And Plato is a little less than 1 mile from the top of its rim down to its current floor. And indulging the assumption that it was probably about the depth of Copernicus originally, that tells us that the layer of lava that filled up Plato is about 1.5 miles deep, which was at one time literally a 1.5 miles deep lake of molten lava. Today, you can see the long shadows that are thrown by the sun from showing the profile of Plato's eastern rim. They can be a nice target for a small scope. The picture at the bottom right, that's for you Arthur C. Clarke fans. That is the crater Clavius, and it's the location of the moon base in the movie 2001. Another site for all seasons, the International Space Station. If you go to spotthestation.nasa.gov and you tell them where you live, what town you live in, and what your email address is, they will send you an email every time the International Space Station is going to be visible from your house. It will tell you what direction the space station will rise from, how high it will get in the sky, what direction it will be headed towards, how low it will be when it disappears, and how long it'll take from one end of the trip to the other. Sometimes the space station will start near one horizon, go across the sky, and disappear as it goes below the opposite horizon. But other times, it'll do what you're seeing in the left-hand picture here. It will start near the horizon, it will go up, and then somewhere along the line, it will just poof, disappear. And what's happening then is kind of neat. The space station is flying into the shadow of the Earth. The sun, as you can see here, is somewhere below the horizon in the direction the space station is coming from. And if you think about what's happening between the sun and the Earth, the sun is lighting up the part of the Earth that is facing the sun, and then the Earth's shadow is extending out into space. At the beginning of the path that we see here, the space shuttle is up above the Earth's shadow, still up in sunlight, which is why it's reflecting back. And suddenly, when it goes out, it's because it flew into the shadow of the Earth. It's not often that you can say that you've just seen Earth's shadow extending into space. If you do see a passage of the space station that does that, look very carefully right at the end, just before it winks out altogether. You will often see the space station get dimmer not go out altogether, but noticeably dimmer for maybe a tenth of a second, a quarter of a second before it winks out. And that is even more neat, because then you can say that you have seen the space station fly into the shadow, not of the Earth, but the shadow of the Earth's atmosphere, the shadow of the air around the Earth. And that is, I think, a pretty neat thing to see. So that's the space station. And that brings us to targets that come back to us every year: meteor showers and stars and deep sky objects. Let's start with meteor showers. Meteor showers happen when the Earth flies through the debris stream that's left by a passing comet. We're going to talk about comets a little later, and we're going to see how they come from above and below the plane of the solar system. So when you see the debris stream, like you see in the left picture here, Earth generally runs through the debris stream only once. And since the debris stream is at a fixed location, Earth's orbit brings it back to that place on the same day, year after year, and that's how that is why meteor showers are predictable and recur every year on the same day. One reason people have trouble with meteor showers is they go out for a little while after sunset and they don't see very many meteors, and they say, oh, this is horrible, and then they go in and watch reruns. Well, the reason they aren't having a very good time with the meteor shower is they're giving up too early. If you look at the diagram on the right, you'll see how the Earth is going around the sun counterclockwise, and it's also at the same time spinning counterclockwise on its axis. Now, if you imagine that the debris stream we're flying into is just to the right of the Earth at the bottom of that illustration, and you imagine that you're at the equator, right at sunset, which is at the left side of that Earth, you start to realize that for the first half of the night, the rest of the Earth is blocking you from most of the debris stream. It's not until you get all the way to midnight, directly opposite the sun, that you can basically see past the rest of the Earth and see into the debris stream. And it's only then that the part of the Earth you're on starts to take a good solid bite into that debris stream and produce a large number of meteors. So for any meteor shower, the prime viewing time is always from midnight until dawn. And before midnight is almost always going to be fairly disappointing. There are lots of meteor showers. They happen every few months, if not more frequently. There is a number that's published called the ZHR, which is the zenithal hourly rate, which is horribly misunderstood by a lot of TV news people, who will tell you, for example, that you will see 120 meteors every hour with the quadrantids in January. That's just not true. The actual number of meteors you will see for any of these showers is always much, much less than the published rate. The ZHR is based on a number of assumptions that seldom, if ever, happen in reality, and the number of meteors you will see in an hour is usually well under 20. We have a nice shower coming up, however, in August. The Perseids on August 13th. We'll have, if you can get to a dark site, you can expect to see as many as 50 meteors an hour, which makes for a pretty good show. The other targets that come back year after year are stars and deep sky objects. And the reason those come back at predictable intervals is pretty much shown by this diagram. You know, the stars are where they are all the time. They don't move, we do. And as you can see, if you look at the arrow pointing from June, in the beginning of the summer, we're looking at the area between Capricorn and Sagittarius. A few months from now, in September, we'll be looking towards the area where Pisces is. Back in March, we were looking at the stars that make up the constellation Virgo. So as we go around the sun, those of us who are on the side of the Earth that's away from the sun, which is to say the people who are having nighttime, are always pointing in a different direction. And that's why we see different stars at different seasons of the year, and also why the stars come back every year predictably at the same time. Now, finding your way around the sky to find the stars that you're looking for takes some doing. If we try to find our way around on the ground, we use states and big cities to help us find things. If you just look at a blank map of the United States and ask, you know, where's Richmond, Virginia, or Kansas City, Missouri? Well, without having the states drawn on there, you're probably not going to get it right the first time. And ask for where's Oakland? Well, it's right next to San Francisco, but if San Francisco isn't on the map, it's not doing you much good. In the sky, we don't have states and big cities, but we do have constellations and bright stars, and those serve the same purpose. So you all have in the materials that George sent around a map of, that looks like this, although it's black on white rather than white on black, that shows all of the targets that we'll talk about tonight, and a set of instructions that'll tell you how you can find those targets in binoculars or a telescope if you have one in your backyard. So let's start into things that we can see in the summer. The most important three stars in the summer sky are called the summer triangle. It's a star called Deneb in the constellation Cygnus, the star Altair in the constellation Aquila the Eagle, and the star Vega in the constellation Lyra the Lyre. And they're important because, first, they're bright. If you look at the right side of the screen, which is the summer stars without the constellation lines there to help you, those three stars, the three bright stars, jump right out at you. We have Deneb up at the top left, Vega at the top right, and Altair at the bottom of the triangle. And if you go out looking for things in the sky in the summer, those are the first three stars you should look for, not only because they're the easiest and brightest, but also because you're going to use those as your reference points to find everything else. Let's start south of the summer triangle and see what we can find. In this part, we're going to talk about the star Antares, which is the bright star at the lower right corner of the, if you look at the left-hand view, it's the bright star right where those three little fingers break off. Constellation Scorpius, which is the constellation that includes Antares, the star Beta Scorpii, which is the top finger of those three fingers. We're going to talk about a star called Rho Ophiuchi, which is directly above Antares. A star cluster called M4, which is just to the right of Antares. And then we're going to go over to the left and talk about the teapot and teaspoon of the constellation Sagittarius, which you can see there to the left of Scorpius near the bottom of the screen. So let's have a look at those. First, we have Antares, Greek words meaning the rival of Mars. We're going to see a little later when we talk about the planets why that's an appropriate name for this star. It looks orange even to the naked eye, and it marks the heart of the constellation Scorpius, which is one of the few constellations that actually sort of looks like a scorpion. It's got the broad flat head up there at the top and the curving body and then the upraised stinging tail at the end. Next, we're going to talk about Beta Scorpii, which is the star all the way at the end of that. If you look at the three fingers extending from Antares, it's the one at the end of the top finger. There is, by the way, a pair of stars just before the end. That's not what we're looking at. That's a different pair of stars. We're looking at the one all the way at the end of the finger, which is called Beta Scorpii, the second brightest star in the constellation Scorpius. And it's a nice little double star. If you put it in a small telescope, you'll be able to separate it into its two components, and it's a nice pretty sight. If we look just above Antares, we're going to find a couple of interesting things. Antares in the left-hand view is the orange star near the bottom of the picture. To the right of it, there's a fuzzy-looking bunch of stars, which is constellation M, or the cluster M4, which we're going to get to in a moment. But if you ignore M4 and look around Antares, you'll see that it's part of a five-sided group of reasonably bright stars. Looks sort of like a lopsided home plate. If you look at the star all the way at the top of home plate in binoculars, you may start thinking that maybe the folks at Disneyland have decided to adopt the bat signal and are sending out a message in space with that little Mickey Mouse looking guy up there. The star is called Rho Ophiuchi, and it's a triple. All three of those stars are related to each other, caught in each other's gravity and rotating around each other. The colors that you see on the left-hand picture, unfortunately, will not be visible in your telescope. The gold color is actually the light of Antares that's being reflected by a cloud of dust that surrounds it. Up above Antares, there's a small blue area around that group of three stars directly above it, and also the bluish gray area around Rho Ophiuchi. That's also starlight, in this case the light of bluish white stars reflecting off dust and gas in those areas. Down on the right hand side of the home plate figure, that red area is a cloud of gas that is actually giving off its own light, because the hydrogen in that area is excited and is generating that characteristic red light. But unfortunately, our eyes are not sensitive enough to see those colors. They only come out in long exposure photos. That cluster just to the right of Antares, M4, is what's called a globular cluster. Globular clusters are very old, 10 to 12 billion years, almost as old as the Milky Way itself. There's about 150 of them, and they are arranged in sort of a sphere that they surround the center of the galaxy. And the globulars are very dense. There's not much space between the stars in them. They are all held together by the star's mutual gravity, and they're close enough that globular clusters stay together for literally billions of years without drifting apart. And if there are any planets surrounding any of the stars in M4 or any of the globular clusters, they have no idea what night is because there are so many stars so close to them. If you look at the cluster in a small telescope, you'll begin to be able to see some of the individual stars near the edge, and then a large mass of unresolved stars looking like a sort of a cotton ball in the center. And again, it's fairly easy to find just to the right of Antares. Now, if we go over to the left, or to the east, that would be from Scorpius, we come to the constellation Sagittarius, which the Greeks said it was an archer, but I don't quite understand how they saw that. You can certainly see a teapot, however, and a teaspoon to go along with it. If we look at the stars themselves rather than the drawing, you can see how they look, and you can even see that little group of stars that sort of looks like steam coming out of the top of the or the spout rather of the teapot. Easy to find in the sky, and tells you where you are. So now let's look at some things that we can see that are in and around the summer triangle. We're going to start up at the top left corner with the constellation Cygnus the Swan. You can see, if you look at the bright star at the top left of the triangle, see it's at the tail of a group of stars that forms a sort of a swan shape. You can see those long wings flapping along, and the long neck down to the nose of the swan, which is a star called Albireo. Bear with me a minute. Got something that's blocking my view here. Let's see if that works. Okay, that's better. So we've got the swan. The center of the swan forms a group of stars called the Northern Cross, which you can see pretty clearly there. Then the star Albireo at the nose of the swan. We go down to from Albireo, if we draw a line down to the bright star at the south end of the summer triangle, down to Altair, we will pass the tail feathers of a neat little constellation called Sagitta that looks like a feathered arrow, and that can lead us over to the left to a little constellation called Delphinus the Dolphin, which sort of looks like a dolphin jumping up out of the water. We'll then follow a line from Altair at the bottom of the triangle to Vega at the top right corner of the triangle, which will take us through a group of stars that form a neat coat hanger that we can see in binoculars. And once we get up to Vega, we'll have the constellation Lyra the Lyre, and a star called the Double Double, which is right next to Vega and is pretty neat to see in a telescope. We'll also see a planetary nebula called M57, which is the Ring Nebula, which is in the bottom of the Lyre. And then we'll go down to the tail of Aquila the Eagle and see a different kind of star cluster called M111, the Wild Duck Cluster. So let's start looking at those. See, the top left corner of the summer triangle is the tail of Cygnus the Swan. You can see the swan flying along, pointing towards the southeast, and the center section is the most prominent, called the Northern Cross, sort of a takeoff on the well-known Southern Cross that Magellan used to navigate around the South Pacific. At the opposite end of the swan from Deneb, you see the star all the way where the swan's nose would be, and that's Albireo, which is a really very beautiful double star. If you can't see it well in binoculars, but even the smallest telescope, you'll be able to split this pair. The photograph does not really do them justice. The blue is much more blue and the yellow is much more yellow. It sort of makes you wonder whether the star is owned by University of Michigan or the University of Notre Dame, since pretty much mimics their colors. And if you don't like either of those teams, you can just call it the Cub Scout star and still be pretty accurate on what the colors look like. If we take a line from Altair down to, or from Albireo down to Altair at the bottom of the southern triangle, or summer triangle rather, we'll pass by a fairly easy to spot pair of stars if you're scanning along that line in binoculars. And that pair of stars is the tail feathers of the constellation Sagitta, which you can fit most of it in your binoculars. It's kind of a neat, it looks kind of neat that way. It does sort of look like a feather or a feathered arrow going across the sky. There is a small globular cluster right along the shaft of Sagitta. I didn't include it because it's kind of iffy. It comes and goes. Sometimes it's impossible to see. Other times it'll jump right out at you. But if you're looking at Sagitta in your binoculars, kind of look along the bottom of the shaft just to see if you noticed a little fuzzball of stars forming a cluster right underneath it. And then just to the left of Sagitta, if you scan over there on your binoculars, you'll pick up the constellation Delphinus, which is that neat little triangle of stars with the tail below it. It is named after, it actually kind of reminds you of a dolphin jumping up out of the water. Now, if we go from Altair at the bottom of the triangle up towards Vega at the top right corner, we'll pass through not quite halfway. You can only see 3 of the stars on this view here, but if we put those 3 stars in our binoculars, we will find a group of stars that looks exactly like a coat hanger hanging upside down in space. If you see it in binoculars, which is the best way to see it, it's really a little bit too large for most telescope fields of view. But if you look at it in binoculars, all those stars that you see in the background here will just be sort of a gray color, and you'll just see the bright stars jumping right out at you as a coat hanger shape, and it's actually kind of amusing. Now, when we get up to the top right corner of the summer triangle, star Vega, if you look at that in binoculars or a finder scope, you'll find out that it's part of a triangle of stars. And if you look at the star at the tip of the triangle, a star called Epsilon Lyrae, also known as the double double. And if you put it in a telescope, it will initially look like 2 stars, 2 pretty much identical stars. But if you can crank the power up to about 300 power, you'll see what you see on the right-hand side. There's actually 4 stars in the system. 2 of them are basically they're perpendicular to each other, and what's remarkable about the double-double is that all 4 of the stars are virtually identical to one another, and the pairs, of course, are virtually identical to each other, other than being twisted in different directions. So it's a very interesting group of stars to examine in a telescope. Oops. Now, if we go down to the bottom of the parallelogram that forms the body of Lyra, the Lyre, and we look almost exactly halfway between the two bottom stars, a little bit to the right of the midpoint of those two stars. With a telescope, you will find something very neat. You'll find the Ring Nebula, also known as M57. The Ring is a planetary nebula, which is what happens when a star like the Sun gets old. As a sun-like star gets old, it starts to use up its fuel. And one thing that it begins to do, it starts to pulsate. And as it pulsates, it gets bigger and it gets smaller, it gets bigger and it gets smaller as it burns different elements in its nuclear furnace. Along the line, the star will start to puff off its outer layers. It's not a big explosion like a supernova. That only happens in much larger stars. But the outer layers of the star will literally break free from the little core that's left. And you can sort of see the core of what generated the Ring Nebula in the center. It's a white dwarf star. It's a body that's no longer creating nuclear fusion, so it's not creating more energy as it goes along. It's still extremely hot and will be hot for tens of thousands of years, but it's just going to start cooling off and slowly dying. Meanwhile, the material that used to be the outer areas of the star has puffed off and is expanding. And right now, the Ring Nebula is more than a light year across. So it takes more than a year for light to get from one side of that nebula to the other. We see it as a nice little, almost like a smoke ring in space. Again, the colors are things that are seen only in long exposure photos. If you see it in a telescope, the ring will be a gray smoke ring. You won't see the green or pink colors that we see in this image, but it'll be very distinct, and will give you a very three-dimensional impression of what happened to that star. Final thing in this part of the sky, we're going to go back to the star at the south end of the summer triangle, Altair, and see if we can maybe find a cluster called the Wild Duck. This is kind of pushing the limits of what you're likely to be able to find from without going to a dark site. But if you are in a place where you can see the two little stars at basically the tail of the triangle there. You see the triangle of stars that includes Altair, and then the sort of handle going down. If you can make out the two stars at the end of the handle, they form the first part of an arc that will lead you to a wonderful, wonderful group of stars called the Wild Duck Cluster. Now, this is not a globular cluster like M4. It's what's called an open cluster or galactic cluster. It's a group of stars that were born at the same time in the same cloud of gas, when that cloud of gas started to collapse into itself and form individual stars. The stars are close together and they're being held together by their mutual gravity, but they're nowhere near as close together as stars are in a globular cluster. So in an open cluster like the Wild Duck, the stars will eventually drift apart. But for right now, they're forming a nice little cluster, and if you look carefully at the bottom right corner, you can sort of see the V-shaped group of stars that made one of the imaginative 19th century astronomers who was looking at it think of the vanguard of a flock of birds in flight, and that's why he named it the Wild Duck Cluster. And it's a nice sight in almost any telescope. It's a little difficult to find in a light polluted sky, but if you can find it, it's definitely worth the trip. So next, let's go to the part of the sky west of the summer triangle. To find our way around there, we're going to need to use something other than the summer triangle. We're going to use the Big Dipper, which you can see in the top right section of these diagrams. And if you use the handle of the Big Dipper as a road map and follow the arc of the handle, it'll bring you to a noticeably bright star that's there at the base of that. It's about midway up and down on the right side of the field that's shown here, at the base of that constellation that looks kind of like a bent ice cream cone with legs. That star is called Arcturus. So you have used the handle of the Big Dipper. You followed the arc of the handle, so you can arc to Arcturus. And once you're there, if you look directly east, which is left on these images, you will find our old friend Vega at the top right corner of the summer triangle. We're going to take that line from Arcturus to Vega, and we're going to divide it into three sections. At the first end of the first section, we're going to find a neat little constellation called Corona Borealis, which is that U-shaped group of stars you can see there, the northern crown. 2/3 of the way from Arcturus to Vega, we're going to find that kind of lopsided crushed box that we see at the center of the constellation Hercules, which that's called the keystone. And along the side of the keystone, we're going to find a wonderful cluster called M13. Directly above the keystone of Hercules, we're going to find another crushed box, which is the head of constellation Draco the Dragon. And one of the stars in that group is a pair of stars, sometimes called the Dragon's Eyes, a nice little pair of stars to see in a small telescope. And finally, we're going to turn the summer triangle from a triangle into an M, and we're going to use that shape to find a star called Alpha Hercules, which is a very neat red and green double star. So let's have a look at these guys. Again, this is getting oriented with use the Big Dipper, arc to Arcturus, look to the left to find Vega, and then we're going to make the 2 stops along the way. First, we get to a group of stars, Corona Borealis. You can put them in your binoculars. You get a nice little U-shaped group, and it represents the crown of laurel leaves that would be worn by a Greek or Roman hero. Next, we have the shape of the keystone of Hercules, that crushed box looking thing in the center. It's too big to put in a binocular field, but we're going to use those stars in order to find a star cluster that's on the right side of the keystone, between the above center of that right, the line along the right side, and it's called M13, the Hercules cluster. It is a remarkable sight in telescopes. It has over 500,000 stars. It is bright and dazzling and complicated. If you look at it very, very carefully, one of the things that you can see is a little 3-bladed dark propeller that you can actually start to see a little bit of in this image. You can see one of the blades near the left-hand side of the image around 8 o'clock. If you imagine a clock's face there, and then if you look from there to the right, you can begin to make out some of the other 2 blades of the dark propeller, and it's magnificent sight in a telescope, and it actually looks pretty good in binoculars as well. So it's a worthy quarry. If we go just directly above the keystone, we get to the head of Draco, the dragon, again, a distinctive group of stars. And we're going to look specifically now at the dimmest of those four stars, the one at the top right corner, or the crushed corner of the box, if you want to think of it that way. And that's a star called New Draconis, sometimes called the Dragon's Eyes. And if you put it in a small telescope, you'll see why that is. They're two perfectly balanced stars looking at you, and although you may not be able to fully appreciate it from the picture, I can certainly tell you that if you're out in the middle of nowhere by yourself in the middle of the night looking at these stars in a telescope, it can be a little bit eerie. It really does feel like somebody's looking at you. So they're nice things to hunt down. Final thing we're going to do is we're going to turn the summer triangle into an M by using two stars, one to the left, one to the right. Left one is a star called Enif, which is in the constellation Pegasus. It's an important star in the fall because it guides us to another very nice globular cluster. But right now we're going to look at the west part of the M, where we have the star Alpha Ophiuchi. Both Enif and Alpha Oph are bright enough that they will stand out in the sky, and you'll be able to form the M without too much trouble. Once we get to Alpha Ophiuchi, we want to go to that star that's up and to the right from it, the one that looks a little bit like it's not exactly bright white. Looks like it might be a little yellowish, and that star is Alpha Hercules, or the head of Hercules. And it's a wonderful star to put in a telescope because it lets you see something that doesn't exist, and that is a green star. There's no such thing as a green star. We could spend a half hour discussing why exactly that is. Just take my word for it. Cannot exist. But the primary star in this pair is brilliantly red, and it's so red that it forces our eye to see the secondary star as green, because that's the complementary color to red. And they're very close together, so it can take a little bit of doing to tease them apart in the telescope, but it's worth the effort because you get these wonderful red and green colors right next to each other, which you don't have a chance to see very often. So that's pretty much the stars and deep sky objects that we can see during the summertime. Now let's talk just a little bit about targets that follow their own schedule, and that brings us to comets and planets. On Tuesday, we're going to be doing a session just on comets on the Naperville Astronomical Facebook page and on the NAA website. The website address, which will also take you to the Facebook page, is contained at the end of the handout materials that George sent you, or you can if you just Google Naperville Astronomy, that will also take you to our website. So I'm going to just say a little bit about comets tonight. If you really like comets, come back and see us again next Tuesday at 7:30. But for right now, let's say comets come from two places, both of them very far away. What are called long period comets, the ones that come back, but it's more than 200 years between visits. come from a place called the Oort cloud, which is sort of the leftovers from the construction of the solar system. It's a sphere of stuff that's almost unimaginably far away. As you can see on the diagram on the right, the Oort cloud goes out about 10 to the fifth, which is 100,000 astronomical units. An astronomical unit is the distance, or the average distance, from the Earth to the Sun. So we're talking about 100,000 times as far from the Sun as we are, or if you want to think of it another way, Mercury's orbit averages about 40 astronomical units from the Sun. So the Oort cloud, we're talking about something that's 2,500 times as far away as Pluto. So it's way out there. Comets break out of the Oort cloud and come hurling towards the solar system and pass through and then go back where they came from, basically. But they can come from any direction. They can come from directly above the plane of the solar system, or directly from the side, or anywhere in between. And as you can see here, the solar system basically is it's basically flat. All of the planets orbit in a plane called the plane of the ecliptic. All of the planets, except with the exception of Pluto, their orbits are within 10 degrees of the ecliptic. And it's basically, we're basically a bunch of marbles rolling around a dinner plate, if you want to think of it that way. The Oort cloud, on the other hand, is a sphere, and the comets from the Oort cloud can come in from directly above the plate, or from the edge of the plate, or from pretty much anywhere. Short period comets, or comets that come back in less than 200 years, come from a much closer but still pretty far away place, two places called the Kuiper belt and the scattered disk. Again, these are sort of the construction debris left over after building the solar system. These are out beyond the orbit of Neptune, beyond the orbit of Pluto, for that matter. And it's sort of a donut-shaped mass of leftover stuff that didn't get used. Comets come to us from the Kuiper belt and the scattered disk, usually within about 40 degrees of the plane of the ecliptic, so they don't have the real steep plunging orbits that some of the long period comets have. Comets are basically thought of as either rubble piles or dirty snowballs. They're not very dense. They have dark rock on the outside and rock and some ices on the inside. The ices that are contained in comets include water ice, carbon dioxide ice or dry ice, ammonia ice, methane ice, number of different frozen things that stay frozen while they're way out there in the outer reaches of the solar system. They're small, comets are, usually less than 6 miles in diameter, and they can't be seen from Earth until they get pretty close to the sun. And the reason is that they only reflect about 4% of the light that hits them. And since they're so small, usually 6 miles or less in diameter, there's not much light coming back. However, when they get within about 3 astronomical units of the sun, or about twice as far from the sun as Mars, they start to warm up, and that ice on the inside of the comet starts to turn into a gas. And like I said, they're a rubble pile, so there's lots of ways for the gas to get out. and it does. The vapor escapes through fissures in the loose structure of the outer comet and carries some. We got the gas coming out. We got some dust particles from the comet's surface coming out, and that material forms a sort of a round shell around that little 6-mile wide comet nucleus, and that shell is called the coma, and that's what we think of as the head of the comet, and it's what we see because those that vapor that comes out is much more reflective than the surface of the comet itself. As the comet continues around the sun, it also develops 2 tails. One is the so-called ion tail that's generated by the solar wind and always points directly away from the sun. It's difficult to see. It's very subtle, but it's always the same sort of electric blue color. We'll talk about where it comes from a little more on Tuesday. The comet also generates a dust tail, which is sort of a trail of the dust that's coming out from the comet along with the internal gases. So as this comet comes around the sun, the point where it reaches its closest point to the sun is called perihelion, and then after it reaches perihelion, it comes back and finds its way back out of the solar system. Now, as most of you probably know, there is a comet that's visiting us at the moment. It's not going to go down as a great comet, but it's not a bad comet. This is it's called Comet Neowise, and we'll talk Tuesday about how it got a name like that. This is a picture that was taken by a member of NAA named Chris Almanza about a week ago. So it's not a bad-looking comet. And on the chart that one of the charts that George sent, the Sky Maps July chart, there's a sort of finder for where the comet will be for the rest of this month. Now, in order to use that, you're going to have to take the page that you got from George and hold it at kind of a funny angle, because you're going to need to look to the sky in the northwest. And when you look to the northwest, you want the northwest to be at the bottom of the page as you're holding it. And if you look up above, that's going to be your northwest horizon. And as you look above the horizon, you'll see, depending on how dark it is where you're at, you may or may not see the stars other than the Big Dipper. You will probably be able to see the Big Dipper fairly early in the evening. In order to see Neowise, you're going to have to look soon after sunset, because it's never going to be very high above the western horizon, and of course it's going to set in the west like everything else does. To give you an idea, on the 21st, the position that's shown there is about 20 degrees above the horizon, and by the 31st, it's only going to be about 25 degrees above the horizon. So you're going to be looking, a lot less than halfway up the sky. You're going to be looking in the lower half of the sky above the northwest horizon, and best bet is probably to use the stars of the Big Dipper as a rough guide as to where the comet's going to be, and scan with, you're going to need binoculars. You're not going to be able to see it naked eye, I don't believe. There were a few days or when it was bright enough for that, but it's faded since then, and it's not going to get bright again. So you are going to need binoculars to find it. And I should also point out the positions that are shown on this chart are showing you where the comet is going to be in relation to the stars at midnight in Greenwich, England, which isn't necessarily relevant if you're not in Greenwich, England. Midnight in Greenwich is 7 o'clock the previous evening here. So basically, if you use the next day's location when you're looking for the comet, you'll be pretty close. For example, if you're looking for it on the 22nd, expect to find it where this chart shows it on the 23rd, and you should be about there. And I hope you all will be able to see it, because comets are fun things to see, particularly in binoculars. They look very good. Like I said, Chris's photograph should give you a good idea of what you're looking for. And that leaves the planets. They also follow their own schedule. We're all going around the sun, but we can be going around at different rates, and where we are, it doesn't necessarily bear any relation to where the other planets are. So they kind of come and go on their own schedule. There used to be a wonderful way to find out what planets were going to be up on any given night. The U.S. Naval Observatory had a wonderful website that they have taken offline for rebuilding. They were supposed to be back online last October, I believe. Then they pushed it to April. And now it's a little unclear when they're going to be back. I believe they are going to be back at some point, so I haven't taken it out of the presentation. And the web address for it is still in the materials that George sent around. So if you check back with them every once in a while, it's a wonderful resource. It's very easy to use, and it will tell you, what planets are visible from where you're at any given date and time that you tell it. So when you do see the planets, what are you going to see? Well, naked eye and in binoculars, you're going to see really two things: bright stars and ruddy Mars. Most of the planets are just going to look like stars. They are bright white. Usually if you look at the star in the sky, or look at something in the sky and think that it's an awfully bright star, 9 times out of 10 it's not a star, it's a planet. They tend to be brighter than most of the stars, and even in binoculars you may not see much detail. The exception is Mars, which even to the naked eye is going to look red. And because Antares and the constellation Scorpius are both in the plane of the ecliptic, Mars shows up near there once in a while. And if it's not happening at the moment, but if a time comes when Mars and Antares are near each other, do make an effort to get out and see them together, because you really will understand why the Greeks named Antares what they did. It's sometimes almost impossible to tell which is which when they're near each other in the sky. In a small telescope, you have a lot more options. Venus and also Mercury, since they're closer to the sun than us, they show phases just like the moon does. And if you look at the diagram on the left, you can see why that is. As Venus goes around the sun, it's always closer than we are. And depending on the angle between Earth, Venus, and the sun, you might see at the far side, you see a full Venus, and when it's much closer, you see those little crescents to left and right of center, and sometimes you don't see Venus at all because it's in line with the sun. The other thing that's interesting about the phases of Venus, and you can get a little sense of this from the diagram on the left, but more so the one on the right, is that the planet gets bigger the narrower it is. So you can see it on the right side, the diameter can be as much as close to 57 arc seconds when you're seeing a thin crescent, and as little as 17 arc seconds when you're seeing basically a half of Venus. And the diagram on the left makes it clear why that is, because you're seeing the crescent when Venus is much closer to us, and the full Venus is when it's farthest away. Usually visible, certainly visible in telescopes, may be visible in binoculars as well, although kind of difficult in binoculars, to be honest. Mars in a small telescope. Mars in binoculars, you're not going to see anything other than anything more than you see naked eye, because Mars is awfully, awfully small. In a small telescope, you will see the ice caps. You will see only one of them, however, because Mars is always leaning towards us, either the top or either north or the south is leaning towards us. So you'll see a little white area either at the very top or at the very bottom of the planet. Now, every couple of years, Mars does come to opposition. It comes reasonably close to us in its orbit, and there is a Mars opposition coming up in the middle of October 13th specifically, will be its closest point. It's not going to be a bad opposition. It's going to have a 22 arc second disk, which is going to be plenty big enough to see some surface detail on Mars. So this September and October and into November will be good times to get a look at Mars in a telescope if you have one available. Jupiter. Jupiter is such a wonderful detailed planet in the big telescope views that you see on the left. Now, you're not going to see that in a small telescope. What you'll see in the small telescope is going to be more like what you see on the right, but you will see the sort of the Jupiter equal sign, if you want to think of it that way, the dark bands across the temperate zones of the planet, which you can see in all three images. And you certainly see the Galilean moons, the 4 moons that Galileo discovered in his telescope in the early 1600s. And more interestingly, you can see the shadows of the Galilean moons if they are crossing the face of Jupiter. In fact, there is going to be a shadow transit will be happening tonight, a little after 9 o'clock, if I recall correctly. But you can see in the image on the right-hand side what a shadow transit looks like in a small telescope. You will see that very distinct, dark, round spot moving across. You won't see it moving in real time, but it'll be moving across the face of the planet, and that's a neat thing to see. Saturn, of course, the rings are something everybody should see live in a telescope. Photographs never do them justice. Again, you're not going to see Saturn the way you see it in the picture on the left, but you can certainly see it in a small telescope as it's shown on the right. You want to look for the rings and the space between the planet and the rings. Sometimes even in a small telescope, you can see some of the shadow of the rings on the planet, or the shadow of the planet on the rings. You can't really see that in the small image here. You can see a little bit of it in the image on the left, but it's something else to look for. Jupiter and Saturn are both easy to find now in the southeast sky. Jupiter reached opposition on July 14th, and Saturn will get there on July 16th. So they're up pretty much all night right now, and really good targets if you have a small telescope. In binoculars, it's difficult, for me at least, to make out Saturn's rings in binoculars. Other people can, who have better eyes than I do. And you can usually see Jupiter's moons in binoculars, but it's worth the extra effort to see it in a telescope. Uranus and Neptune, nothing, you will not be able to see them naked eye. You sometimes can see them in binoculars, but not very satisfying views. And even in a small telescope, you're not going to see anything more than what you see on the right. Although the robin's egg blue color that you see with Uranus can be pretty neat to see in a telescope. And finally, I'm going to end with what I think is the best planetary view ever. Unfortunate we aren't doing this live, because it's always fun to ask people to guess what this is. So I'll give you a minute to think about what you would guess if you had to. I'll give you some clues while you're waiting. It was a photograph taken in May of 2010, and it was taken by a spacecraft called Messenger just before it entered orbit around the planet Mercury. NASA asked Messenger to take a minute and look back and just take a picture of us all. And this is what Messenger sent. That is how Earth and the Moon look if you lived on Mercury. If you wake up any day and feel like we're just too special for words, this is a good image to think about. Put you back in our role in the universe. And with that, I've pretty much finished up. If you have a telescope and want to learn more about how to use it, there are lots of books out there. There is one, however, that I think is head and shoulders above the rest. If you are looking for a book to guide you on using your telescope, and that's Turn Left at Orion. I am not related to either of those guys, and I don't get any money for any of that, but it's the only beginner's guide that I know of that actually tells you how to find things. Most of them tell you how neat it'll be to see this, that, or the other thing, but they never tell you how to find them in the telescope. And finding them in the telescope is the hard part, folks. This book does that, and it does it very well. So if you are only going to get one, that's the one I would get. Where else can you learn more? Well, at the moment, NAA is not having in-person meetings, so you can't. So I can't recommend that you go listen to that handsome feller over on the image on the right. We will eventually go back to that, and everything we do is all of our meetings are open to the public and free of charge. In the meantime, however, if you check the calendar on our website, again, it's the website address is in the materials, or if you just Google Naperville Astronomy, you'll get to us. We are still having 2 meetings a month. We have our meeting the first Tuesday with an outside speaker, usually somebody from, always a professional, and someone from Fermi or Northwestern, University of Chicago, somewhere like that, who will be talking about some, usually their own work that's ongoing, or some other topic in astronomy or astrophysics. We also have a second monthly meeting on the third Tuesday of each month when we have a member of the club talking about more practical amateur astronomy things. And all of those are now being done virtually on Zoom. You can watch them either on the Facebook page or on directly on the website. And if you see something in the calendar that you like, by all means, feel free to join us. And eventually we will also get back to having public nights at our observatory, which is on the west edge of Naperville. We have a couple of telescopes in the buildings. We have a 16-inch in the building in the dome, which is a visual scope that you can get up on the ladder and have a look through. The roll-off roof building on the right has a 12-inch 12-inch scope in there that is, rather than being used with an eyepiece, it's hooked to a 40-inch black and white monitor on the wall, so people can, group of people can see things in the telescope at the same time. As I said, we're not in the in-person business at the moment, but when we go back, we'll go back to having, as we have in the past, 2 public nights a month all year round. And in the meantime, we are doing virtual observing again on Zoom. If you follow the Facebook page, we'll announce when we're going to be doing it. We've done several sessions with stars and deep sky objects, as well as some sessions with different parts of the moon and solar observing as well during the daytime. So with that, I think do we have some questions as we went along? No. Okay, I'm looking at no open questions. If anybody has any that they want to ask now, feel free. Okay, I see a raised hand, but I don't see a question. So I'm not sure.
What is a good entry-level telescope?
Well, that's sort of like asking
for children.
What's the best kind of food to eat? It depends on so many things. If you go to the NAA website, there is a page on there about factors to consider in choosing your first telescope. There's a lot of things that that you should think about. It's really, I need to sit down and talk to you about who you are and what you want to do and why you want to do it, kind of things, in order to answer the question.
Okay, thank you.
Sure. Was I the guy? Okay, somebody's asking if I was the guy at the Indiana Dunes with the telescopes. No, I was not. But I've been other places. Let me see. Is the Oort cloud homogeneous in every direction? I haven't the remotest idea, Joe. I do not know. I suspect the answer is no, but I do not know the answer to that. And any other questions out there? All right. Well, unless anybody else has anything, Jim or George, anything to add? Okay, I guess then we'll call it a night. thank you all very much for coming. It's been a pleasure. I hope you enjoyed it.